Assalamualaikum and hi everyone! Welcome to our MAT183 video assignment. We are going to present about related rates in application of differentiation.
This video will be presented by our four new teams, Enisa Huda, Dayang Nur Aminira, Nur Rabiatul Adawiyah, and Nur Ifa Shakira. So, let's get started.
What is differentiation? In calculus, differentiation is one of the two important concepts apart from integration. Differentiation is a method of finding the derivative of a function. Differentiation is a process in maths where we find the instantaneous rate of change in function based on one of its variables. The most common example is the rate change of displacement with respect to time, called velocity. The opposite of finding a derivative is anti-differentiation. If x is a variable and y is another variable, then the rate of change of x with respect to y is given by dy over dx. This is the general expression of derivative of a function and is represented as f prime x equals to dy over dx, where y equals to fx is any function.
So, there are 5 applications of differentiation: related rates, Rolle's theorem, mean value theorem, maxima and minima, and determining increasing and decreasing function. So, in this case, we chose related rates to solve our problem. Right, what is related rates? Related rates is a process of finding derivative of rate of change of a function. Related rates is a problem involving two or more quantities, their corresponding rates of change with respect to time. Related rates determine how fast or how slow a certain quantity is changing using the rate of change of the second quantity. There are 5 steps of finding the related rates. First, you have to decide what are the two variables. Second, find an equation relating them. Third, you have to take d over dt of both sides. Fourth, plug in all known values at the instant equation. Last but not least, you have to solve for the unknown rates. In these related rates, we use chain rule and differentiate the equations, which is implicit differentiation with respect to time.
We are going to solve together our often next related rates problem. This one, another classic that appears on exam. We will use our 4-step problem-solving strategy for related rates problem to tackle this since it works every time. So the question is, a ladder is leaning against a wall. The ladder's base is sliding away from the wall at the rate of 2 meters per second. If the ladder is 10 meters long and slides away from the wall at a constant rate, how fast is the top ladder sliding down the wall when the base of the ladder is 6 meters from the wall?
Let's start with the first step. We first draw a picture of the situation, which is the ladder leaning against the wall. Once you draw the picture, you might notice right away that the ladder forms a right angle triangle with the floor and the wall. And this geometry of the right angle triangle will be crucial to our solution and is a big clue to the approach we will use. The ladder is 10 meters, a fact that we'll set aside for the moment as we think about what is going on. As the time passes in the problem, base of the ladder slides horizontally along the ground, which causes the top of the ladder to move down the wall. Notice that the ladder never loses contact with the ground or the wall. Now, of course, if the ladder slides along the ground faster instead, then it slides down to the wall more quickly too. The rate at which it slides horizontally is thus somehow related to the rate at which it slides down vertically, and our job will be to find the exact relationship. Let's assign some variables to mark the location of the ladder's end at each moment. We'll use x for the horizontal distance from the wall to the ladder's base, and y for the vertical distance from the floor to the ladder's top. The problem tells us the rate at which the ladder's base slides horizontally, that is the rate at which is dx over dt, the rate at which x varies with respect to time t. We are told that the rate is 2 meters per second. The problem then asks us to find the rate at which the ladder's top moves down the wall, and so we want the rate dy over dt, the rate at which y varies with respect to time t. Specifically, we have to find the rate at the instant when x is equal to 6 and the base is 6 meters from the wall. So we are given dx over dt equals to 2 meters per second, and we are asked to find the value of dy over dt. We thus need the relation between dx over dt and dy over dt. To find that, we back up a stage. At first, need to develop a relation between x and y, and that's the second step of our strategy. To write an equation that relates the quantities of interest, in this case between x and y in any related rates problem, you'll use one of 4 approaches that you need to know to complete this step. For this latter problem, the right triangle we've drawn tells us that we'll use the Pythagoras theorem to develop our question. You will find that you use the Pythagoras theorem a lot in the solution to related rates problem, and it should be your go-to choice anytime you have the right angle triangle and you need to relate the length of the two legs. The key thing is realize that as the ladder slides down the wall at every moment, the z and y legs of the triangle form a right angle triangle with the 10 meter slides as the hypotenuse. Hence, at every moment, x squared plus y squared is equal to 10 squared, which is equal to 100. A common mistake at this point is to substitute 6 meter for x, but you can't proceed correctly if you do that. Instead, because the location of the letters best changes as the letter slides along the ground, we have to leave x as a variable for now. We'll substitute x is equal to 6 meter at the end of our solution. By contrast, the letter's length is always 10 meter, and so we use that as a fixed value in our equation here. And that's it. We now have the relation need between x and y, and so we're done with the second step of our strategy. That brings us to the third step. Take the derivative with respect to time of both sides of the equation, remembering the chain of rule when we do so. We then have d over dt of x squared plus d over dt of y squared equal to d over dt of 10 squared. The derivative of 10 squared or 100 is equal to 0 since that the derivative of a constant. On the left hand side of the equation, we have the derivative d over dt of x squared, which is 2 times d over dt plus the derivative of d over dt of y squared, which is 2y dy over dt, and that's all equal to 0. Why are those dx over dt and dy over dt terms there? So let's check it out.
Are you wondering why the dx over dt and dy over dt appear? The answer is chain rule. The key thing to realize is that we are taking the derivative here with respect to time. While the derivative of x squared with respect to x is d over dx times x squared equal to 2x, the derivative of x squared with respect to time is d over dx times x squared equal to 2x times dx over dt. Similarly, the derivative with respect to time of y squared is d over dt times y squared equal to 2y times dy over dt. Okay, why are those dx over dt and dy over dt terms there? To answer that, let's go back to Pythagorean equation of time. Move position, change as time passes and the ladder slides down the wall. But now, let's explicitly show the time dependence of both x and y, which are both functions of time. So we will show them as such to emphasize the point. Let's again take the derivative with respect to time of both sides of the equation. So we have d over dt of x as a function of t squared plus d over dt of y as a function of t squared equal to d over dt times 10 squared. That last term is 0 again since the derivative of a constant is 0. To remind ourselves that both x and y are function of time, then when we take the derivative, it will be 2x times dx of t over dt plus 2y times dy of t over dt equal to 0. We apply chain rule here. Now, notice both of these chain rule terms have to be here in order for us to relate dx over dt and dy over dt as we actually set out to do. With that, remember that we explicitly wrote both x and y here as functions of time in order to illustrate why these chain rule terms are here. Typically, you would never write all that out and instead you just write like as we did before, which is 2x times dx over dt plus 2y times dy over dt equal to 0. So, with that, let's return where we were. For the next step, solve for the quantity you are after. The question is asking us to find dy over dt at the instance when x equal to 6 meter and dx over dt equal to 2 meter per second. So, let's solve the preceding equation for dy over dt. Isolate the 2y times dy over dt term on the left and move the 2x times dx over dt term to the right side of the equation, where it becomes negative. We can then divide both sides of the equation by 2y to get rid from the left. And we are left with dy over dt equal to negative x over y times dx over dt. Plus, to complete the calculation, we need to know the value of y at the instance when x equal to 6. Let's check it out in the next slide. So, the next step is begin subproblem to find the value of y at the instance when x equal to 6 meter. We can find this value by using the Pythagorean theorem. After substitute x equal to 6 into the equation, we can get the value of y equal to 8. Next, substitute all of the known values into the equation marked in previous page. So we have negative 6 over 8 times 2. So we get the value of dy over dt equal to negative 3 over 2 meter per second. Note that the negative value indicates that the top of the ladder is sliding down the wall in the negative y direction.
From this problem, we can conclude that the rate at which the top of the ladder is sliding down the wall depends on the height of the ladder on the wall. It is also important to identify which variables are changing and how are they related to each other. And also, the differentiation with respect to time or other variable required application of chain rule since most problem involve several variables.
That is all from us. Thank you.